All right, welcome to my lecture on the normal distribution. I'm going to focus exclusively on the normal distribution now, and we're going to jump right into it. So the normal distribution, it has an equation that's given by this, and there's a whole bunch of symbols there, so you're probably wondering what they represent. So this letter mu, that represents the population mean, and it's estimated by the sample mean. Okay, it's also where the peak occurs in the Bell distribution, and I'll show you the Bell distribution, that bell shape that we've talked about. And this Greek symbol sigma, that represents the standard deviation, and it tells you how spread out your data is. And these things really stand out in a graph of this function for different values of the mean mu and different values of the standard deviation sigma. So let's look at these graphs. Here's a whole bunch of different graphs of the normal distribution. Let's see if we can make this a little bit better. Okay. Okay. So let's look at this blue, let's look at this blue curve, and it has the smallest standard deviation. All of these curves, this blue one, this red one, and this yellow gold one, they all have means of 0. The difference between this blue and this red and this yellow gold is the standard deviation. The one with the tallest peak has the smallest standard deviation. That means that it's the most concentrated around the mean, and that the mean is the most likely outcome. As the standard deviation increases to the red one, so the red one has a standard deviation of 1, the blue one has a standard deviation of has a variance of 0.2, and the red one has a variance of 1. Okay, so the variance is a square of the standard deviation. As that increases, the standard deviation, or equivalently the variance, because they represent the same thing by taking the square root or the square. Okay. As the standard deviation increases, you can see the mean becomes slightly less likely. There's more spread in data. The mean is always the most likely outcome. Okay. And as it increases to this yellow gold one, it has the most standard deviation, and likely outcomes would be more outcomes further from the mean become more likely. So if you look here, the area under the curve represents the probability. So the area between 2 and 3 for this yellow gold is this little area right here. And that's a bit of area. But for the red one, it's a very small amount of area. It's not as likely. And the area for this blue one is very, very teeny. It's nearly 0. Okay. So the standard deviation controls the spread of the data and makes larger values more likely. Equivalently, if you decrease the standard deviation or the variance, it makes larger outcomes from the mean less likely. And remember, we measure events that are far from the mean in terms of z-score, the number of standard deviations that an observation is from the mean is the z-score. So the larger the z-score, the less likely for greater than events. And the smaller the standard deviation, the less likely for less than events. Okay, so just a little bit of review there on z-scores. And they will be very, very useful in this chapter. Okay. And this green curve right here, it has a standard deviation, a variance of 0.5. And its mean, it's different. Its peak occurs not at 0 like the other 3 curves, but its mean occurs at -2. So mu here is -2. And so the mean is the average, and it's also where the peak is, where the center is. all of these are normal distributions. They're symmetric and bell-shaped. So they all have that characteristic, and we're finally seeing their graph and their equation that represents them. Okay, so why would we be interested in normal distributions? Well, they're useful for a lot of things. A lot of things seem to have somewhat of a bell shape, and here's an instance in which it could be very useful. So it says what body temperature is considered a fever, and it says the CDC considers a person to have a fever when he or she has a measured temperature of 100.4 Fahrenheit. Okay. And it says, hey, you'd like to take your temperature to check if you have symptoms for COVID-19. Okay. So, as you might guess, body temperature is normally distributed. So it obeys a bell curve, and there is data to back this up. So it says the normal body temperature is 98.6 degrees Fahrenheit. And this is well documented. And it says that the sample standard deviation is 0.73 degrees Fahrenheit. So I'd like you to calculate the probability that someone has a temperature that exceeds 100 degrees Fahrenheit. Okay. So the body temperature of an individual is a very important predictor for being able to distinguish if someone is having irregular body functions, if they are suffering from a cold or possibly COVID-19. So the normal distribution is extremely important. And one way in which we're going to do this is we're going to calculate, well, if they have a normal body temperature, they're not sick, their body temperature should be 98.6 degrees Fahrenheit. And what are the odds that someone that is not sick has a temperature in excess of 100 degrees? Okay. So if you want to calculate this probability, you need to use a really good calculator, or you can use your table in the z-score that's in the back of your book. Okay. And our goal is to calculate this probability. Okay. So there's an important fact that's really important to calculate these probabilities, and it says if x is normally distributed with a mean mu and standard deviation sigma, then the z-score, which is this thing, we've seen that before, is normally distributed, but now it has a mean of 0 and a standard deviation of 1. This is really important if you intend to use your tables in the back of your book to calculate probabilities. Okay. Now, what I have listed here are tables that are similar to the ones that are in your textbook. And if you're using the Sullivan textbook, you can see table 5. Okay. And it lists the cumulative probability, which is this. It's the total probability up to the value of little x here, and little x being that. Okay. This is what we aim to calculate. I have graphed that density function, and it has a mean of 98.6, and I want to calculate the probability that our observation is greater than 100, so I want all this area that is greater than 100. Okay, and that represents probability. But in your probability tables, if you're using section 5, what you can calculate is the probability x is less than 100. So if you want to calculate the probability x is greater than 100, you have to use the complement rule. You do the complement of 1 minus this. Okay, so let's proceed to calculate this. Okay. So if we want to calculate the probability x is bigger than 100 right here, I'm going to take the complement rule. And this probability right here, probability x is less than 100, can be calculated from your table. Okay. Then the next step would be to take the z-score. So I subtract the mean, which is 98.6. I divide by the standard deviation of 0.73. And one thing that I want to say about the standard deviation is that the standard deviation, I calculated that from real data, and it estimates the standard deviation as 0.73. So it's a reasonable estimate. Okay. So I take this z-score, and I get a number for this. When I crunch this number, I'm going to get 0.09724, and I have to take 1 minus that, which is 2.76. And you would have to use this table in the back of the book. So you should have a standard normal table. It should say standard normal on it. It's in table 5 for you if you have the Sullivan book. And you need to go down to find your z-score and across, okay? And since this number is a positive one, you wouldn't want to use this z-score here, but you'd want to use this one, this positive one, okay? I'm going to show you how you could use this now using a calculator, and what you would see is that if you used a calculator, okay, so remember our mean is going to be 98.6, and we want to calculate, our standard deviation is 0.73, okay. Here is the online stats book, so you can see the web address there, and in this section they have a section called calculators. These are the statistical calculators they have. I'm going to go to the normal distribution calculator right there, okay. It tells us to enter in our mean, which is 98.6, so I can just enter that in. This is going to be 0.73. And I want to calculate the area above 100, okay. So let's just calculate that, and it says it's 0.0276, so 2.76%, and that's exactly what we have for this problem, okay? And so that's another way of calculating probabilities. We could just use that online calculator instead of using the table, and that is sometimes, you know, a bit easier. So it's totally up to you. You can use this calculator to answer these questions. Okay. Now, if you wanted to calculate this number, you could do that using this table, okay? And the z-score that you get, so let's just calculate this z-score, would be 1.91. So this number that I'm about to erase would be 1.91, okay? And if you wanted to use a table, 1.91, what you do is you go to a z of 1.9, so that's right here, that's 1.9. Then you go across till you hit the second decimal of 0.01, and that would represent 1.91, and this would be 0.9719, okay? And we get 0.9724, that's because I used a different calculator. It's off in the third decimal place, but the calculator that I used is slightly more accurate, but they're relatively similar. Okay, so you should get very similar answers. It would not affect your answer by much. Okay, and you should get, that's how you'd use the table, is you go to 1.19 in this z-score, 1.9, then you go across to 0.01. Okay, So using the table, as you can see, is a little bit more involved, but it's up to you how you want to calculate your probabilities. I personally prefer the calculator, but I'm okay with either one. Okay, so here's another example, and it says the heights of men aged 25 to 35 are normally distributed with a mean of 68 inches and a standard deviation of 5 inches. We want to calculate the probability that a randomly chosen man has a height between 65 inches and 73 inches. Okay. So here is the probability we want to calculate. We can either use a really good calculator or we can use the z-score and a table. Okay. Either one is okay. This is our desired probability. So here we want to calculate it's between 65 and 73, and the mean is 68 with a standard deviation of 5. So here 68 occurs at that peak. We want to calculate between 68 and 73. And so this probability is not listed in the table. It's only the less than probabilities. So here's a less than probability. This represents the probability x is less than 73 is this. This represents the probability x is less than 65. That's here. And if I subtract the two, I get exactly the area in between. And that's the desired probability. Okay, so here is how we do it with our table. Okay, so I want to calculate this probability. We saw that the two graphs, that this probability breaks down to the probability x is less than 73 minus the probability x is less than 65. So we go about by calculating these less than probabilities by taking z-scores if we're using the table. So I subtract the mean of 68, divide by standard deviation of 5. I do that on both sides. So here I take 73, I subtract 68, I divide by 5. This gives me a z-score of 1 minus a z-score of negative 0.6, and I subtract that. If I want to find these values in the table, I go back here, so I find 1, z-score of 1 would be 0.8413. That's that value right there. Then I find the z-score of minus 0.6. So minus 0.6. So here it is, and there's no decimals after the 0.6. So I take this first value, that's 0, minus 0.60, and that's 2743. Okay. And there's 2743. I get 57.6%. Now, if I want to use the other method, I want to use a calculator. Okay, I'll enter the mean, 68, standard deviation is 5, and I want to calculate the probability that is between 65 and 73, so I'll go between. And I get 0.5671. Okay, that's the same answer that we have before. Okay, so two ways of doing the same thing. You can use the table, you can use the online calculator, whichever is most convenient for you. Okay. Now here's one more example. It says the diameter of pipes is manufactured to meet a 3.25 inch specification. That is when you buy this pipe from the store, it says, hey, this pipe is 3.25 inches, so you need to buy the right fittings, right? And they need to meet that specification. Otherwise, no one's going to buy that product that doesn't, meet specification. Okay. Now, when you produce a part, nothing's ever perfect. So there's imperfections. And the diameter may or may not be produced exactly at specification. And So the diameter, when you pick up a random pipe off the production line, might be slightly off from 3.25 inches, but hopefully not too much. Okay? The data shows that the mean is 3.25 is reasonable, and that the amount of variation, and remember, variation controls how much deviation or how spread out the data is from the mean. Okay, so we'd really prefer if we had the smallest standard deviation possible. Okay, but the data shows the standard deviation is 0.04 inches. Now, parts must be discarded if they're bigger than 3.3 inches or smaller than 3.2 inches, which is reasonable, right? They need to fit a fitting, okay? And they need to be able to connect and work with the other parts. So the question is, well, what proportion of parts must be discarded? Okay, so probability of discarded, that means that x is less than 3.2 inches or x is greater than 3.3 inches. This is 1 minus the probability of x being between 3.2 and 3.3. So in other words, it's 1 minus the probability it's not discarded. And we've done this probability before. And I apologize, this should be 1 minus this. Okay. And this should be the probability z. We take the z-score, so we subtract the mean of 3.25, divide by the standard deviation of 0.04, and we do 3.2 and subtract 3.25, the mean, and divide by the standard deviation of 0.04. This should give us 21.1%. And let's just calculate this. Okay. So if we were to calculate this, standard deviation is 0.04. This is 3.25. We want the probability of discarded, which means it's outside 3.2 or bigger than 3.3 inches. And if we recalculate, this is 21.1%. And that's exactly the number we got here. Okay. Now, one way of viewing this, would be it's 1 minus the probability. I just forgot the 1 there. 1 minus this probability, and we can write it like that. Okay, and that is 21.1%. Okay. Okay. So here's another situation in which the sampling statistic comes up. The normal distribution comes up, and that's with the sampling statistic. A sampling distribution of a statistic represents the probability distribution for all possible values of the statistic computed from a sample mean. The probability distribution of a statistic represents how likely it is to observe a sample with certain parameters. Okay. So there are two sampling statistics that we deal with. One is when the data is numerical, and that's just the sample average. Take all your data, add it up, divide by the number of data points. Okay, that happens to have a normal distribution. There's another sampling distribution, and that's the sample proportion. That's the total number of individuals that meet the characteristic divided by the total number of individuals in the sample, or total number of data points. Okay, the sample proportion is typically normally distributed, but it needs to meet a few requirements. Okay, and we're going to talk more about both of these next time when we talk about the central limit theorem. Okay, so thank you.